Hello and welcome to this video on memory. So we've talked a little bit about memory in the past, but today we're really going to talk about memory because memory is really very important. So memory at its core is essentially just storage within your computer. And typically we're talking about storage of binary digits or bits, because modern computers typically store most of their data in binary. So in a normal conversation you might talk about a modern computer having 4 gigs of memory. And this is really just 4 gigs of binary digits for your computer to play with. Typically when we're talking about memory, we're usually talking about a specific type of memory called RAM. RAM stands for Random Access Memory, and this essentially just means that it should take approximately the same amount of time to access any two portions of memory, even if these bits aren't physically close to one another. So I could access some bits at the start of my section of 4 gigs, or I could access some bits at the end of my section of 4 gigs, and it should take approximately the same time to get both of those bits back from memory to me after I've requested them. And this property really does matter, because if instead most computers had sequential access memory, then programmers would have to think a lot more about memory accesses, because we no longer have the guarantee that any two equal-sized memory accesses should take approximately the same time. So as I just alluded to, most data your machine is dealing with is just stored in binary in memory. And one of the important things to realize about binary data is that it doesn't really mean anything without any context. So if I give you the binary sequence 00000000, what does that mean? Well, if we interpret that as an integer value, it could represent the number 0. If we instead interpret this set of binary digits as a character though, it might be the ASCII null character, or it might be some character in some other text encoding that isn't ASCII. Maybe this is actually a character in some arbitrary text encoding where this value represents the lowercase letter a. This binary sequence might not even be data to our program as we usually think of it. For example, it might actually be the binary sequence for some instruction that's supposed to execute on our CPU. Or maybe in some image format, this sequence represents a red pixel. You can see from this that binary sequences are just binary sequences. We can't really say anything about what they mean without context. Now back to C. The C standard is actually pretty lax about where compilers want to store data, so that particular implementations can make things fast for their platforms. So a question like where is the data for local variables in C stored isn't particularly easy to answer because it depends on your compiler. That being said though, a lot of implementations for modern architectures do a lot of things similarly. For example, a lot of modern implementations store local variables or block scope variables in memory on a stack. If you're not familiar, a stack is a first in, last out data structure, which means, as it sounds, that the things you add to it first actually come out of it last. So for example, if you push the element A, then the element B, then the element C to a stack, and that's what we call it when you add things to a stack, we call it pushing to the stack. Then when you pop from the stack, which is the opposite of pushing, so when we take elements out of the stack, you will take them out in the order C, then B, then A. And because of this kind of behavior, stacks are very well suited to the way scope works in C. So for example, if we enter a new scope, we may have some local variables in there, so we can push their values to a stack data structure in memory. And then when we leave the scope of those variables, we can just pop them off the stack and sort of discard them in memory, and then we can get ready to add new things to the stack if we need to. File scope variables, on the other hand, are typically dealt with differently. Because they don't have this kind of disappearing scope behavior, there's no real incentive to store file scope variables on a stack. As a result, modern implementations instead commonly reserve a section of data inside the executable file inside our actual final binary for these variables, so that when the binary for our executable is loaded into memory to get executed, we can just use some of that memory to store file scope variables. The same thing is also often done with constant string values instead of just baking them into the calculations like you might do with constant integers. Some implementations also use the stack to pass function parameters, by the way. So when we call printf, for example, we might push our parameters to a stack, and then let the code of the printf function pop those parameters off the stack to use. Block scope variables and function parameters are also commonly stored in registers, by the way, which if you recall are just very fast portions of memory within the CPU. Regardless of these compiler implementation specifics though, most compilers will at least store some variables outside of registers in memory. And when we're talking about memory, we can reference specific locations in memory. So let's imagine for a second that we have a memory unit that can store 8 bytes. Then it makes sense to want to be able to talk about each of these 8 bytes individually. For example, maybe we're looking to store an integer in each of these 8 bytes, and we want some way to reference each individual integer. Well, the easiest way to reason about this is just to give each byte a number. So maybe we have byte number 1, byte number 2, byte number 3, byte number 4, byte number 5, byte number 6, byte number 7, and byte number 8. In computer science though, sometimes we like counting from 0, because counting from 0 has some really nice properties to it. And so that's what we typically do, so in this case we'd probably number them 0, 1, 2, 3, 4, 5, 6, 7. And in the case of a larger section of memory, we can just do this for all of the bytes in, for example, 4 gigs. And you might think, well, why stop at numbering bytes? Why not number individual bits so we can reference bits individually? And while that's kind of a nice idea in theory, it doesn't really work out so well in practice. Because if you have 4 gigs of bits to manage, you're going to end up with quite large numbers required to number each bit. Now we call this number that identifies a particular byte of memory a memory address. And actually there's a little bit of extra complexity here that I'm hiding from you, because most modern operating systems also implement virtual memory systems, which means that memory addresses don't necessarily relate directly to physical locations in memory. At the end of the day, it's one of those systems that still works great if you don't know it exists, so you don't really need to worry about it. So with all of that theory out of the way, let's actually try and write some code. So the first C operator that actually relates to all this that we're going to talk about is an operator we've actually already used, which is the address of operator. And this is expressed using the ampersand symbol, just like we've used for reading input into variables via scanf. So for example, if we create an integer variable here called data and we can initialize that to 5, then if I type ampersand data, which we can read as address of data, then this expression is going to give us the memory address of this variable data. And we've used this for scanf because if we give scanf the location of our data, it can write into that location and change the data that our variable holds. Whereas if we just pass scanf data, we're just going to pass it the value 5, which isn't particularly useful for it. And actually we can use printf to see what this value is on my machine to actually view the memory address value. So if we just call printf here, and we can use the %p format specifier for a memory address type, a pointer type, and we'll discuss more about pointers in a second. So if we compile and we run, you might think, Joe, what the heck are you talking about? That doesn't look like no number to me. Well, you're wrong, it is a number, but it's a number in a format you might not be used to. So instead of writing the address values in decimal, we typically write them in hexadecimal. This is a number system with base 16 rather than base 10 like the decimal system. So if you want to count to 16 in hexadecimal, you're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and then you go to what looks like 10, 1, 0. But you don't super need to understand this to use memory addresses. So just to make this a little more friendly, if we just clear that and go back, if we change our format specifier here to LU, which is the format specifier for an unsigned long type, and then we cast our memory address here to an unsigned long, so that this expression is now of type unsigned long rather than being of a memory address type, then we should be able to see things in decimal. There we go. So this value is the memory address for our data variable this particular time around on my particular machine. Note, by the way, that this kind of casting is generally speaking unsafe because of type sizes. So we don't know, for example, that our memory address will be able to actually fit inside the size defined for our unsigned long type. And by the way, I think we've covered this before, but long is just another integer type in C, which can often represent bigger numbers than the int type. And we can check if this operation is unsafe on my particular machine. We want to check if the size of the memory address of data is equal to the size of our unsigned long type. And if we compile and run, hey, it turns out that cast was actually completely safe on my particular compiler setup. Back to our code though, to accompany our address of operator, we also have a dereference operator. And the dereference operator essentially gets the value at a particular memory address. So this is kind of the opposite of the address of operator, because if we dereference the address of something, we're going to get the value of that thing. So for example, if we dereference our memory location of data here, which we can do via the asterisk symbol, which is the dereference operator in this context, then we can compile and run that, and you'll see we get 5. Because we got the memory location of our variable using the address of operator, and then we went ahead and grabbed a value at that memory location using the dereference operator. So essentially the two just cancel each other out here, and it's the same as just writing data. So okay, this is kind of useful for explaining why things work the way they do, but how is this practically useful? Well, I can show you why this is useful using pointer types in C. So first off, if you think about it, the dereference operator has to know what kind of thing is at the address it's trying to dereference. Because it's going to need to do different things if it's dereferencing a 1-byte char as opposed to a 4-byte int, for example. As a result, memory addresses in C have types associated with them. For example, our memory address of data here has an int type associated with it, because it holds a memory address that points to an integer value. And we can express this type in C using an asterisk also. Note that when we use the asterisk to write pointer types in C, this has nothing to do with the asterisk we use for the dereference operator. We're not dereferencing anything. Just as the asterisk for the dereference operator has nothing to do with the asterisk for the integer multiply operator. So we can declare a variable with the integer pointer type. First off, we type the type that we're pointing to, so int in this case. Then we type our asterisk to indicate that this is a pointer type. Then we type the name of our variable as normal, so let's call this one pointer. And then that's the declaration done. And we can initialize this variable as normal too. In this case, maybe we want to initialize it to the address of our data variable. So now we've declared an integer pointer variable called pointer, which we've initialized to the memory address of our data variable. So anytime we write pointer, it now refers to the memory address that our pointer variable holds. In this case, the memory address of our data variable. So if we want to printf the integer, which is the dereference of our pointer variable, that's going to dereference the memory address of our data variable. And so we expect to see 5, the value we initialized our data variable to. So if we compile and we run this, excellent, we get 5. Similarly, we can actually create pointer types to pointer types. So we can declare a pointer to an integer pointer like so, and let's name this one pointer, and we can initialize it to the address of our pointer variable. The 2 asterisks in the type definition here indicate that this is a pointer to a pointer. So our pointer variable here holds the memory address of our pointer variable, and our pointer variable holds the memory address of our data variable. So if we dereference pointer, then we're going to get our pointer variable, in other words the address of our data variable, and if we dereference that, then we're going to get the value at our data variable, which should be 5. So if we save, and we compile, and we run, excellent. Now a lot of people get confused by pointers, but there's really no need to. You've just got to think about it logically and think about what memory addresses are being held by what variables. Now if we go back here, and let's just get rid of pointer for now, what happens if we actually just initialize our pointer to a numeric value? So let's just say we initialize our pointer here to the memory address 0. Let's get rid of our data variable and let's try and dereference our pointer. So what we're doing here is we're trying to read an integer value from the memory address 0. Well, let's see what happens here. If we go and we compile and we run, oh dear. Our program exited with a segmentation fault because we made a bad memory access. In this case, we're probably not allowed to read from that memory address. Invalid memory accesses in C are very common causes of problems. So let's look at a less contrived example. If we keep our pointer around and let's just create a block here, and inside this block we're going to have that integer data again, which we're going to initialize to 5. And then what we're going to do is we're going to set pointer to the address of our data variable, just like we did previously. And then down here we're going to printf the dereference of our pointer variable, which you may think would give us the value at our data variable, which in this case is going to be the value we initialize the variable to, which is 5. However, if you recall, we cannot guarantee the existence of block scope variables after their scope ends. So once we encounter this closing bracket here, our data variable could be destroyed entirely. And so it's dangerous for us to keep the memory address of that variable around, because we may not even have permission to access that memory anymore. We might get a segmentation fault. But the worst part is if I go and compile this and run it, despite what I just said, it worked. And really this is just pure luck. We still happen to have access to that memory address and it still happens to hold the value 5. And variants of this extremely dangerous code plague a lot of badly written C projects, because they can create issues that only occur some of the time if you get unlucky. Instead of getting a segmentation fault here, we might have just got some other value back, like 15. And that could cause huge problems. But anyhow, let's get back to the practical side of pointers. It's kind of hard to show you the real power of pointers without going into some more complex code. But the feature of pointers you'll often want to use is the fact that you can actually change the memory address of the pointer. Because it's a variable, remember, not a constant. So we can change the thing that a pointer points to. So maybe we have an integer variable a and an integer variable b. One is initialized to 5, one's initialized to 10. And then we have an integer pointer called value or something. And we can initialize that to the memory address of a. So then we can printf the value at a by just dereferencing our pointer. Of course, we could just write a here. But then what we can do is we can change the value of our value variable, which is an integer pointer, to the memory address of b. And then we can copy and paste this exact same line, and it's going to output the value of b. And this might also seem a little bit trivial, because we could just write a and b, but the fact that we can use the same line of code to output the value at that pointer, but be referring to different variables, is one of the many reasons why pointers are immensely useful. And of course we can check this works, and of course it does. We can also write through pointers, by the way, there's nothing scary about that. So before we dereference value to output b here, we can dereference value to change the value of b, so we can say, well, dereference value equals 5, and then of course that's going to set b to 5, and thus we're going to print a 5 twice instead of 5 and 10, so we can try that. There we go. And just keep in mind that pointers are extremely powerful, and we'll definitely be talking about them in future. So last up in this discussion of memory and pointers, we're finally going to address strings. So we've used textual strings like hello world, but what type of data are these in C? I mentioned earlier that strings in C are usually stored statically in some portion of the executable that gets loaded into memory, and we've talked a bit before about how strings are just stored as sequences of characters, and it turns out the type for just a constant string in C is a char pointer. And this char pointer just holds the memory address of the string, which as I've said is typically in some section of our output binary. So we refer to strings unlike other types through this layer of indirection. String-like things can also be stored in other ways in C, and we're going to talk about those in future, but usually when we talk about a C string, we're talking about a char pointer. And of course we can verify this is true, so let's create a char pointer variable, and we can just call it string, and let's initialize it to the string hello world. Then if we call printf, and let's use the printf format specifier for a string, then we can just pass in our parameter, which is the variable named string. And no, we're not going to dereference that because we want to pass in the char pointer, not just the char, because strings in C are primarily char pointers. And we can try that, so we can compile and run. Awesome, I'm not lying to you. If you think about this, strings don't actually have a fixed size. So how does printf know when to stop reading our string? How does it know that our string isn't actually hello world exclamation mark and then whatever byte values happen to follow that in memory? Well, it's because strings in C are null terminated. What this means is when we write the string hello comma space world exclamation mark, the string that actually gets stored is that followed by a null character, which indicates the end of the string. In many encodings, including ASCII, this null character just has the byte value 0. And again, I can actually show this, so if we actually just put a 0 byte after the word hello in our string, then printf is going to think that's our whole string. And we can write this null character via the \0 escape sequence, and so let's try that. If we compile and run, aha, we only get hello. So there we have it, traditional C strings are null terminated. Similarly, we can use this property to count the number of characters in a string. At some point soon you should be able to use iteration to write your own code which counts the number of characters in a string before the null terminator. I don't think we've quite gone over everything to do that quite yet though. My hint for anyone that wants to try is pointer arithmetic, but actually there's a C standard library header file we can include called string.h, so if we just paste this line in there, include string.h, and that has a whole bunch of C standard library function definitions relating to strings. For example, we just talked about counting the number of characters in a string. We can use the strlen function to count the number of characters in a null terminated string. So if we output the %d number of characters, and we compile, oops, of course this should be an unsigned long type format specifier, and we recompile and we run, we can see that strlen has counted the number of characters before our null terminator as 5, which is correct, HELLO, 5. And if we take out our null terminator and we recompile and rerun, it now counts the number of characters in our string as 13. So that is the end of this video. We have covered quite a lot. Most importantly, the basics of memory, pointers, and strings. So that is the end of this video. I will catch you next time.